So I'm told I'm supposed to take this mic with me since I tend to move around a lot while I speak. We have spent, my collaborators and I, Tom Caswell and Ken Lauer, and some others that we work with on related projects, have spent the last year working on a project that's exposed us to some aspects of the core Python language that those of us who come from the NumPy numerical side of things often don't get to play around with as much. And so in this talk, I'd like to share some of that with you. The work here is roughly a year or less old, so it's all pretty new stuff, but we'd be very interested in new collaborators and hard questions that you might have about the approach that we've tried out here over the last year. So we come from the National Synchrotron Light Source 2 at Brookhaven National Lab, which is a Department of Energy user facility. There's a great variety of science that's done at NSLS2. It's a facility where, if you're not familiar, users often from academia, but also from industry, would come in for, let's say, about a week, and that have access to hardware and to the X-ray synchrotron source that you see pictured there in the big ring, and they take their data with their samples, and then in the past they go home with a pile of hard drives and analyze that data. So there's a huge variety of different experiments, some of them well-established pipelines, some of them ad hoc experiments with innovations and new techniques occurring in real time during the visit. So our role is to try and corral all of the data that's being generated through these visits into some form where we're capturing more about the semantics, more about the user intention, and in general try and enable the scientists to have an output that is more reproducible. To go into a little more detail about what we have right now and where we're going, we have 12 semi-independent research groups about the size of a small academic research group of scientific staff, and then again these visitors coming from the outside that take some portion of the available X-ray beam time. We're going to scale up to 60 semi-independent groups in very roughly 5 years, depending on how the funding rolls in. That's going to put us at about 19 petabytes per year, it is estimated. And I said expensive pixels up there because I distinguish it from like a Google image search crawl or something like this. All of the pixels that we're analyzing in this kind of image analysis have a lot of information around them and generate a lot of money poured into not only the X-rays, but potentially samples that are being analyzed. We are surrendering the idea of ever settling on a common agreed upon data format. We think that may be a fool's errand for us, but we'd like to at least do what we can to capture the metadata in a structured and validatable, if extensible form, and to at least be able to open the data, so to understand how to open the different kinds of file types, and ultimately get someone an array in memory, which is something that everyone can work with. So we're storing the metadata, we're storing the raw data, or at least references to data stored in files on disk. Our goals for this software project, and by the way, we have a mandate from the management that we can basically start from scratch. So we're not, we're always burdened with old code. We're never going to totally escape that. But we're supposed to have all of the scientists using the same data collection stack, which would be the first time that that's ever been done, I think, at a facility like this, and really unify things to a greater extent than they've been unified before. There's a lot of buy-in to use open science and the SciPy stack, and we want our tools to integrate with that very well. We want to support live streaming data analysis. And to get a little more specific about the metadata and our interest in it, we need to capture a detailed snapshot of the hardware, right? This isn't simulation work, so you really need to go out of your way to understand the initial conditions and all the different things that might affect the outcome. And then we also want to know the semantics of the scientist's intention, not just what bits they tweaked or what knobs they turned, but what they were doing in the course of that experiment. That could be valuable for automating downstream analysis. And with all this metadata, we'd like things to be searchable, the idea of Google your data and potentially searching across the entire facility, all kinds of different techniques, and all kinds of very interesting machine learning applications might come out of that. And then as much as possible, as we design this framework, we'd like to give people the full power of the Python language. We're trying very hard not to accidentally invent a sort of private NSLS2 language. There are unavoidably some assumptions and some sort of domain-specific language patterns that are creeping in, but as much as possible, we just want this to be a light framework that gives you things but doesn't restrict too much what you can do within Python. So to get right into it, this is a typical, almost pseudocode data collection script that someone might have used at an earlier facility. So they're looping through different motor positions, and each time they move the motor to a new position, they take a picture. Missing from this is much semantics about what that motor is for, or what the detector is for, or any kind of human readable name identifying them. We also don't know why this experiment was done, what sort of technique it was. It's up to the scientists to write their data out to some obscure CSV format or text file that only they probably understand, or their postdoc who's going to be gone in 10 years. And then if they're careful, they put all this inside of an error handling loop that will leave the hardware in a safe state upon completion of their experiment. And what we'd like to do is separate the logic of the experiment from these I/O concerns and from the cleanup concerns, and to add some meaningful human-readable metadata and to really encourage that, and as much as possible, provide it by default. To make this possible, I just want to briefly show how we relate to hardware, how we talk to the actual motors and detectors that are collecting our data, and then I'll more or less dispense with this and move on to experimental control and the actual logic of the science experiment. So we have a device abstraction layer that we've called OFID, and the job of OFID is to basically make all hardware look the same as much as possible. That from this sort of physicsy point of view, there is no difference between a motor and a temperature controller. That these are just things that you move, right? So who cares about the details? And of course, you need to provide a way to access those details when things break. But when things aren't broken, having a high-level API with which to address hardware lets us write the logic of an experiment once, moving in some, say, complicated trajectory, and then apply that trajectory to all kinds of different unforeseen hardware, because the hardware has a way to look normalized, to all look the same. Our library OFID talks to EPICS, which is popular in the synchrotron community, but we've written it in a way that we hope it could be extensible to LabVIEW or any other protocol that someone might be interested in talking to. I want to show one more slide about the devices here. So they're hierarchical, and again, they add sort of human significant names to these things. So here's a multi-axis mirror. It's a device. It has 3 motors in it called X, Y, and Z. If you've ever written with Traitlets or with SQL Alchemy, this kind of pattern will be familiar. We magically can see those names, X, Y, Z, or X, Y, and pitch, and they show up when I read the mirror object. We have different readings, and they're all hierarchically sorted into dictionaries like this with nice, meaningful names. So this is how we're talking to hardware. And now our new style acquisition program, contrasted to the one I showed earlier, is quite different. There's no I/O. There's no hardware safety cleanup or interruption recovery stuff written into this plan. This is just a Python generator that yields messages or instructions that are going to tell our run engine at the bottom of this slide what to do. And then the run engine will reach out and actually perform the execution of this plan. So we're moving people away from free-form scripts that do unrestricted things, which is kind of an imperative style, to call back to the keynote this morning, to a more declarative style, where you're yielding out instructions that we interpret and then we have more control. So for example, we do all of the I/O for free, and we notice every time you move a motor or adjust a temperature controller, we can maintain a list of those things so that upon exit, we can make sure everything is stopped or put into a safe state. Now, all this stuff you get for free by formulating your experimental logic as a Python generator that yields these specific things. So in case anyone hasn't seen yield or yield from, hasn't had a reason to use those yet, I just wanted to quickly give those people a chance at following what I'm about to say next. So this is a Python generator. It yields, which is basically a function with multiple exit points. So we could say next, and we get the value 1. Next again, we get the value 2. Or we could listify the generator, and then we get all of its values. So it's a function that you can keep asking for new values from, very roughly speaking. Yield from is a way of dispatching from inside one generator to another generator. So when I listify H, we get 0, we get the values from G, and then 4, all as a flat list here. If you want to know more about this, I very strongly recommend James Powell's talks on generators. He's given a talk called Generators Will Free Your Mind many times all over the world. Each one has more alarming examples than the previous, in no matter which order you watch them. So the rest of this talk, let me just quickly glance at the time here. Good. The rest of this talk is going to be on the run engine, this magical thing that consumes a Python generator, and I say takes care of all your problems and makes them go away. The neat implications of expressing a science experiment as a generator and some sort of interesting things you can do with that, and then how reliably capturing the state of the hardware and the semantics of the scientist's intention are critical to providing enough information to create a reproducible workflow and an automated workflow downstream in analysis. Okay, the code for the run engine is something like 1,000 lines, and so I wasn't going to give you a tour of that, but we've reduced it through partly the hard work of my collaborator, Tom Caswell, to progressively more complicated versions of the run engine that hopefully you'll be able to think are helpful in understanding this. So the plan that the run engine is consuming is emitting these instructions every time it yields, and the instructions we call messages. A message is just a Python named tuple with 4 components. All right, so the command tells us what you're going to do, and that's the most important part for the semantics. So you could be setting a temperature controller or a motor to a new position. You could be telling the run engine to sleep for a couple seconds while the sample thermalizes or something like this. Then there's a target object, if this is something that's happening to a piece of hardware, like a set. There are positional arguments and keyword arguments that will then get passed through to whatever function is actually doing the work here. So here's the message object in Blue Sky. And you can see the message is sleep for 1 second. There's none because there's no hardware target for this kind of command. So here's the simplest possible run engine. We start with a function map that maps command names, sleep, and print to little functions that will sleep and print, logically enough. And then the core of the run engine itself here is a loop that loops over the messages in a plan, tells us which one it's processing, just so we can follow along here, finds which function the command in the message is referring to, and then executes that function. So our plan, called sleepy plan, is going to sleep and then print hello world, as it has done here. So we'll run it again for fun. Sleep, hello world, and then there's the print hello world. Please clap. Here's version 1, a run engine that supports adaptive plan logic. So here's where it gets just a little bit more interesting. Now we have a while true loop that's going to iterate through our generator, and we're using here a coroutine function of generators, a coroutine method of generators that is going to send the result from each computation or each processing that the run engine does back to the plan. So now the plan doesn't have to be a list of pre-formed instructions. It's just a thing that generates instructions one at a time. So I send the run engine an instruction. It sends me a response. I can make a decision about what to do next based on that response. And you can see how this would support adaptiveness in the plans and some pretty cool applications. So to demonstrate this, we're going to have a little sum command that is not a real thing that we use, but it's nice for demos, that will sum the arguments of the message. We go into the next thing here. Here's our adding plan. So it begins by yielding a sleep message just to do something to get started. Then here's where it's different. It yields a sum message with 3 and 4 as the arguments. And the flow here is this message goes to the run engine. The run engine processes the sum message. And then the run engine sends back a result. And at that point, the result then gets assigned to this variable. So the syntax looks a little funny if you haven't seen it before. The thing on the right is sent to the run engine, and the response goes into the variable on the left. So we can watch how this works. Process sleep, process sum. The run engine prints, the plan rather prints that it received the result 7 back from the run engine. So now let's actually do something with this. The adaptive adding plan will keep adding 3 to the result that it gets back to the run engine until that result is greater than 8. So this is all the same, minus the fact that we're putting the result here on the left. And then when the result is greater than 8, we break our infinite while loop. Boom. So there's adaptive logic. And what you should imagine, and toward the end I'll actually show you an example of this, is the applications this could have. You could have the run engine giving you the latest reading from a detector and then do perhaps even a numerical integral based on that reading and then make a decision about whether your scan is done yet or what step size you want to take next. You can get some very rich logic in here. Yeah. Yeah, that's a good point. Thank you for speaking up. Okay, so we'll look at the control flow from the run engine side. So in order to seed a coroutine in Python, you have to send in none first. So we send in none, and that cues the plan to give us its first message. We get the message on the left, we look up which command that is, just as before, we process the message, and then we get that result. We go back to the top of the loop, we send the result back in. Does that answer your question? Great, thanks. Okay, so version 2 is pretty simple. We're just going to take version 1, and instead of a function now, we're going to need a class, because a class lets us inspect some internal state of the run engine from outside of it. And so I've taken what used to be the function run engine and turned it into a callable class, so that when we make an instance of run engine, we can call it, and then that does exactly the same stuff. So the body of the code here has not changed one bit. We've just changed it from a function to a callable class. And I'll just confirm that it still works. Great, that's good news. Okay, so that was set up for version 3. A run engine that finally is going to invoke the promise in the title, which is async IO. The same loop, the same main loop, is still iterating through the plan. But while we have that loop running, while we're processing through the instructions in the plan, we also want to be doing other things. We want to be managing IO. We want to be watching for the user to hit Control-C or in some way initiate an interruption in the processing of our plan. And we want the ability to freeze the execution of the plan and then resume it. So this is really, really useful for scientists. And I would say that this, above all, is the feature that has convinced them that we're not crazy and that they should maybe take this seriously. If they're watching this, hopefully they agree. The use case here is that you could end up running something overnight that gets interrupted because the X-rays have stopped running and you need to turn them back on. or you need to resume the scan until the X-rays have turned back on, and you can get good data on your sample again. And so we need some way for the run engine to support interruptions and then recovery from interruptions. So quickly, we've refactored these functions that do the logic as async IO coroutines, which are like tasks that can be scheduled on an event loop. And now when you call, we create a task in async IO. We run this loop. And at this point, the user has lost control, and async IO is in charge of everything that happens from this point until the task is done. And the run is basically the task that is given to async IO. So here we're still looping through our messages as we've done before, but that loop is now managed as a task in async IO, which, not shown, is also managing other things concurrently. And it still works. So now we've gotten to the point where we cannot show the run engine's complexity on a slide, and we're going to jump to the real run engine imported from Blue Sky. So here it is. And we're going to make it verbose, and we're going to teach it about our toy sum command. And now I want to do a real demo that I need 2 hands for. Hang on. So you can see the run engine is in a pause state. There's all kinds of garbage here telling the user what's up. If we come back, we can resume. And the run engine has maintained a cache of all the messages that we've told it so far and can cleanly resume, output the data in a safe way, and give us our scan. We can pause programmatically in the middle of a scan like this. We can tell the run engine, if we're on the second iteration of this thing, let's just pause and let the user decide whether they want to continue. So the run engine paused, and the user can resume. We haven't told the plan, through the plan, we haven't told the run engine anything about where it's safe to resume. So the run engine is assuming that if something goes wrong, I'm just going to go back to the beginning and start again. So we add a notion of checkpoints, which are just little semantic messages that say, every time we begin this for loop, that would be a safe point to start again if we happen to get interrupted. Otherwise, this is the same plan as before. Sweeping, we've got pauses in here. Let's look at what this does. So we get a pause. We made it up to received the number 4. When we resume, we start from where we left off. So this is a really powerful idea. You can specify in your scan whether it's safe to resume from an interruption. Perhaps you just have to stop. You have to abort. And if it is safe, where exactly is a good place to roll back to? So this is the other option. We ran our pausing plan, we paused, and we decided we're happy with what we have so far, or something went wrong and we just want to quit. We can abort. So I could give a half-hour talk on the internals of how this resuming and aborting is working, and I think I'm maybe breezing through it a little bit, but the takeaway here is that, are we going to 220? What's that? Oh, okay. Cool. So I'm sorry. The important thing here is that the user has a couple options for how to exit and to resume at various times. I'm sorry, I derailed myself there. So let's demo another thing we can do with plans. We have a problematic plan here, and the problem with this plan is that it raises an exception in the middle of the plan. So it says processing sweep, then the word error is printed, an exception is raised, which bubbles up through the run engine and then lands to us here. Now we have the option to insist that the run engine performs some cleanup on the way out of this plan. So if an exception is raised inside the plan, inside make safe, the finalize wrapper will ensure that the cleanup plan is run no matter what. So finalize wrapper catches any errors coming from inside its plan and runs the plan from cleanup before then re-raising the error that arose from the problematic plan. What could be simpler? So the use case for this is I'm running a scan. I don't either trust the author because I don't understand the internals, or I'm worried that something might go wrong, and I want to ensure that, say, I move my motors back to safe positions before I quit, or something like that, right? That's very useful. And so here we can see we sweep, we get the error printed from our plan, but first we process this sweep for 2 seconds message from the cleanup, and then we get the statement, everything has been made safe. And then finally, the exception is re-raised. We can even catch problems that happen in the processing of those functions that the run engine is executing. So what if I give time.sweep a string as an argument? That's going to be an exception bubbling up from the built-in time library, we can catch that as well. First, let's watch it raise. So I try to sweep for A, and we get a type error coming from time.sweep. But if we make it safe, the cleanup is run, and the motors are, say, returned to their safe positions before the plan ends. This is a reckless plan. The reckless plan catches exceptions coming from inside the run engine, say, ignores them, and politely lets us know at least that it's ignoring them, because errors should not pass silently, and then sweeps. So before I wrap up, I'll talk about one more feature of the run engine, which is that it's taking care of the I/O for us here, and I haven't really mentioned that yet. I've shown that we can do some crazy things with generators, and that because we're specifying our plans through generators, that the run engine knows the semantics of what it's doing. But what does it do with that information? Well, it collates all of the readings that are part of the plan into dictionaries that we validate against a JSON schema, and then we dispatch these dictionaries to subscribers, which are just arbitrary Python functions that take in a dictionary as an argument. These subscribers could be blocking, so if you're, say, writing the data into a database, that would be a really critical activity, and you may want to block on that. But if you're plotting, say, you might tolerate faults in the plotting code and continue the scan in spite of that. Am I getting the hook here, Matthias? Okay, cool. Okay, sure. So, yeah, just in it, write a few more times. There we go. That's the punchline. So the dictionaries that are coming out of the run engine get printed in this very nice table because it is a function that takes in dictionaries and prints a table. You can likewise do very nice plots that would show up in real time. So there's all kinds of things that you can do with the data that are coming out of this. I'm sure I've left plenty of questions, so I should leave time for people to ask one or two. Thank you. So we have, I think a fair estimate is roughly 100 people have used it, and it's been in like production for, let's say, 6 months. It's very new. Right. It was definitely building the airplane while while it's taking off on the runway, for sure. Okay, shall I hand it over?
What if you want to interrupt a specific plan? For example, can you have two run engines going next to each other? One that monitors the sample and one that does task. Can you interrupt only one of those two?
You would generally not have two run engines running in the same process. If you want to be doing concurrent things or asynchronous readings, that's something you can support as part of one running plan. Okay, thanks everyone.